All right, so now we'll have John give us a, is it working? Some slides. Oh, yeah, it's working, okay. Okay, so John will give us a talk. So this, for a little bit of context, I don't know if John is planning on going into it, but this is a recent paper that was published this year. That was a revisiting of a paper that had been published, I don't know, 30 years before that.
96.
96, so 28. So we just thought this would be great for the juniors to get a bit of perspective, zoom out a little bit on how we actually know that we form QGP in the collisions that we have delivered from RHIC. So hopefully that was a transition, and now John can take it away. Thanks, John.
Thanks, Isaac. Yeah, Bill mentioned earlier that he was one of the first on STAR. In fact, he was the first postdoc or young person or junior on STAR. The other person was an engineer and myself. So anyway, and I will violate all of Kong's rules, all three of them in particular. I tried to delete every third slide. It didn't work. So I'm assuming that you're pretty much aware of the RHIC program and STAR results, although I'm not really going to assume any of that. But, you know, when I mentioned JSI and RAA and all that stuff, I'm not going to define any of those variables, okay? All right, so I need to give special thanks to Bernd, my co-author. This was just published and put online about a week or two ago. And it is addressing a paper that we published before RHIC started running in 1996 by a similar name, Search for the Quark Gluon Plasma. And the current paper is Revisited, okay? That name, Revisited. And the iconic figure there showed 8 different variables as a function of the energy density and how they might behave. And this wasn't just Bernd and my work, this was the community's vision kind of put down conceptually in a graph. So maybe that satisfies one of Kong's things. Anyway, so I think what I want to do, I will end up telling you, going through this list in the first half or 3/4 of the talk, and then I will mention the ones that we didn't anticipate. And there are a lot more that we didn't anticipate. Now, whether they're really signatures or not, that's still to be determined, and that's why all of you are here. Okay, so I think the main thing is to first define the energy density, and one can go, and I have a lot of references here because I'm not going to really tell you what every single thing means, but you can go back and look. But this is the Bjorkane energy density, and it's easy to calculate. And so what we have done is looked at the initial energy density as a function of the center mass energy in heavy nuclear collisions, and you see that it increases dramatically above 10 GeV per Fermi cube for LEC energies. And also it drops very low here as you go down below the beam energy scan energies, down to the lowest beam energy scan energies. So let me start with strangeness. This was probably the first that was predicted, and I show you here the strangeness chemical potential on the left, and it's in the way we expected it to behave was that it would drop to near zero as you cross over into the quark gluon plasma region of energy densities. On the right, you see the strangeness chemical potential, the strangeness fugacity, or the strangeness saturation factor, which we expected to approach 1 if you have a quark gluon plasma. So that's what that plot really tells you, and there were a number of publications in the early 80s, early to mid 80s, which basically showed that if you take QQ bar annihilation or gluon-gluon fusion, for the most part, you should, above about 150 MeV temperature, create a deconfined medium or increase or saturate the strangeness in the medium, and it will stay there for some length of time, a few times 10 to the 23rd, which was expected to be what was needed if you made a quark gluon plasma. Now, results from the SPS, STAR, and let's say RHIC and the LHC have now shown that if you take strange baryons, starting with singly strange up to triply strange omegas, that as you increase the number of participants, which usually increases with centrality, that one could go from light systems to heavy systems, and that you get an increasing ratio relative to PP, for example, as you go and increase the number of strange quarks. And that is true also STAR has seen this, and this has been seen in ALICE, to where it looks like it starts to level off. And so this is one indication, in fact, that strangeness appears, well, first of all, is it enhanced, but is it, in fact, saturated? One can go and take the chemical fit using grand canonical ensemble, and that's the dash curve here. And one could plot this versus data from the AGS, SPS up to LHC. And it looks like in the region of RHIC, these are RHIC data points, mainly STAR, that in fact it does saturate. And this really does confirm the expectation, in fact, that strangeness is saturated. One can also look at the omega to pi ratio, and plotting that same curve, you see the same thing happens for, starting with PP, it's way down here, but it saturates up here at the higher energies of lead, and it's somewhere in between for protons on lead. Now, quarkonia, or let's say charmonium and bottomonium, that's CC bar or BB bar resonance states. One thought initially, and this was in 1986 by Matsui and Satz, that the J psi should be suppressed in the quark gluon plasma due to Debye screening. And so here is plotted in the dark curve the first excited state of the J psi versus the ground state, and the first excited state should be suppressed more easily because it's less tightly bound. And then, on the other hand, the ground state of the epsilon, which is BB bar, should in fact, the ratio of that to the ground state of the psi, because the psi is suppressed, should increase. So that was the prediction, and I'll show you in a minute what was seen, but let me just give you this graphic that, if you place the CC bar, BB bar in a deconfined medium, then the pair can't always find each other, and that would be what's called Debye screening in a way. And so therefore you'd have a suppression of them compared to just making them in hard scattering. There's also the prediction, and it is borne out in the next couple of slides. I'll show you that, as a function of temperature, that the psi 2s is most easily dissociated than the higher excited states of the epsilon, then the ground state of J psi, then the epsilon 1s, the BB bar, is more tightly bound than the CC bar. Okay, and then so, first thing we see is if you take RAA of the J psi, that the J psi is suppressed as you increase the centrality of the number of participants. And that, in fact, the suppression is fairly similar if you go from SPS to RHIC, that's these points here, at mid-rapidity, and then the forward rapidity points are slightly more suppressed, all right? That's also seen at the LHC, where here we have the J psi, both from Alice and CMS, and then the first excited state, actually the psi 2s, you see that's slightly more suppressed. So in fact, it's seen to be suppressed both at RHIC and LHC, but the point I want to make here is that the RHIC suppression of the J psi is down here for the higher PTs, and that the LHC suppression is not as strong as at RHIC. All right? I leave that to you to think about. It's in the quiz questions. And anyway, okay. And there's good reason. Let me put it that way. The epsilon 1s, that's BB bar ground state, is similarly suppressed. That's these points here at RHIC and LHC. However, the excited states, the 2s and the 3s, are slightly more suppressed at the LHC than at RHIC. The other thing that we wanted to find out about, and still to be investigated even more at EIC, is in fact whether there are cold nuclear matter effects in Corconia in particular here. What one sees is the RPA, RDA, and RAA. The heavy ion data is suppressed, as we know, when you look at the J psi, but when you look at D gold and P gold from Phoenix and Star, respectively, you see a slight effect here below about 2 GeV and PT, and this appears to be the cold nuclear matter effect possibility. And if you go and look at the same thing at the LHC and P-lead for the J psi and the epsilon, and you do calculations, first of all, you see the same thing. Of course, the blue points are the lead-lead suppression, and then these black and gray points are P-lead, and basically at different rapidities, but one sees that at the low PT, there is a suppression in P-lead at the LHC, and that these models show that there must be an effect there as well and attribute it to cold nuclear matter. This is, in my view, about all the data that I'm aware of on such cold nuclear matter effects, and will have to be investigated more. Okay, temperature. Well, you know, temperature was really the first thing we thought about in terms of the equated state of QCD matter. You know, whether we reach a high enough temperature, whether the number of degrees of freedom increase dramatically, meaning you don't just have nucleons, but you have quarks and gluons. And so that's why that would increase as you go up. So if you increase the temperature, you would in fact expect to be able to increase the temperature, and it might even flatten out here for the case when you have both quarks and gluons and hadrons together. This would be a mixed phase. Well, you know, you can try and measure thermal slopes of spectra to get the temperature, but of course they're corrupted because, you know, it's just the final state and you have expansion. On the other hand, there are very beautiful data initially from STAR when RHIC was running, as RHIC has been running, but it was put out first before the LHC data. And so here you see the nice fit in the thermochemical model, which gives you, for various models, about 155 MeV. For the various yields is a function of rapidity. I'm already losing my voice. Let me get a throat lozenge. Okay, so STAR has a very similar plot with similar variables that predict it. Now, one can also go and look at the invariant mass spectrum for lepton pairs. I don't know, is this paper now published from STAR where these electron pairs now show a temperature of around 300 MeV. Anyway, that's a question I have that you can tell me about. But what's shown here is a function of the barochemical potential is the freeze-out temperature on average and the initial temperature on average, and the temperature that one gets from the intermediate and low mass dilepton invariant mass spectra, both in Na60 here and from star here. And so this is a kind of pseudo QCD phase diagram. Thanks so much. And then let's look at the radiation of the QGP as such. What's predicted here is that, of course, you get more thermal photons if you have a thermally radiating system. So that should increase with energy density. But of course, direct photons carry the momentum, the energy, and the information from the entire evolution of the system, so it's dynamic. And the collision, the expansion changes. The photon spectrum gets blue shifted because of this expansion. And in fact, there's a contamination of the thermal photons by first of all, photons that might be created in the initial state, and also photons from the Hadron gas phase. So these interpretations are quite model dependent, so one has to take them a bit with a grain of salt. The direct photon spectra from Phoenix, after subtraction of the N collision scaled PP, is shown here. They get, for the most central collisions, 240 MeV or so in temperature. And at the LHC, if you look at the data from Alice, there's a slight enhancement here over interpretive QCD calculations, and that difference gives one about 300 MeV or so for the most central data. So we're talking about temperature ranges from 240 to 300 or so that appear to be extracted from the radiating quark-gluon plasma. So there was also a prediction that there would be disoriented chiral condensates. And this is a long-standing prediction. So if the system is supercooled and it cools down very rapidly, there may be domains that have different chirality, and therefore they would have different ratios of, the various types of particles. And this is what was called a disoriented chiral condensate. Actually, it was first predicted in the 70s by Veneziano, I think, and then Krishna and Frank Wilczek picked it up again in the early 90s with their paper. But, none have been found so far. There were, I think initially at the Bevelak, that was one of the reasons and motivations for actually looking at the ratios of neutral to charged pions. Nothing has been seen, and it looks like, as we've seen since, the fireball actually evolves adiabatically and not just a sudden, breakup where these domains separate with different charge ratios. So I'll leave it at that, and I'm sure that DCCs will continue to be looked at as one analyzes data. There's something I'll mention at the very end, which is disoriented isospin condensates, but I'll mention it only briefly. That's something that has arisen very recently, kind of starting from the whole search for DCCs. So here we have chiral restoration. Lattice QCD identifies, that there's a crossover transition, and I know that, with the beam energy scan, one is trying to find, what are the parameters, whether there's a a rapid, other than just a crossover, even a first order phase transition. So if the temperature is below the critical temperature, then a chirocondensate approaches its vacuum value, whereas if it's above, then it approaches zero, meaning that chirosymmetry is spontaneously broken, and if one could see results of that, it would be quite interesting. What it really means is that these excitation modes, that differ by parity will become degenerate, like the A1 and the rho, or some others. Well, in looking at dielectron spectra, Phoenix and STAR have done a wonderful job. STAR in particular, if one looks as a function of collision energy, one sees what initially was seen at the SPS, this enhancement of low mass dilepton pairs. That you see this above the cocktail, which the cocktail being all the other possible ways to make dielectron pairs in this mass region. And no matter how you look at it, there's definitely an enhancement there. That has been interpreted already at the time of the SPS measurements as being the broadening of the rho, which has to do with the rho sitting in a medium that is most likely deconfined. Okay, and then I just point out Alice has done the same thing. And let me move on to interferometry, because initially we were thinking, okay, if we have a mixed phase, that the out versus side sizes for two-plan interferometry would give us some indication of the formation time. And if that's true and there's a mixed phase that's kind of prolonged in the expansion, then one might get some behavior that looks like this. Now, let me back up a minute, and that is Hembury-Brown, one person, and Twist, another, together published this paper of, okay, if we correlate bosons, two photons, so they took two coherent beams of light, they said we would get an enhancement and be able to measure its properties. This was further looked at in the, I would say, 80s and 90s, where one could look at identical pions, which are bosons, and try and measure the size of the emitting source. There's a nice pedestrian's guide here to interferometry and HBT that Bill Zeitz published. So what was seen was the formation time plotted here as a function of the density, let's say, the charge density to the 1/3, all the way from AGS experiment 895 up through, this is SPS energies, up all the way through RHIC and LEC, that this is more or less a straight line when you plot it versus the 1/3 of the charge density per unit pseudorotary. The other thing that's interesting is that this was recently published. If you take the R out versus side, which is an indication of the formation time, so just think of it, if it's expanding towards you, you get more of a measure of the formation time than it's expanding away towards the side. And that's what interferometry will give you, that there in fact appears to be a peak here at somewhere around 10 GeV or so. And this is a combination of experiments that show this, and this could give us some indication that there's some incompressibility around TC during the hadron emission. So I refer you further to this publication here, which puts that data together. Now, parton propagation was an interesting topic early on because most of us were more nuclear physics oriented and hadn't thought much about how a parton propagates through anything, be it a nucleus or nuclear matter, which we were hoping to make. And as you know, the RAA, at the time we thought, okay, for particles and jets, it could either increase or decrease as a function of the energy density. And so Yorkane, back in 1982, said, look, it's going to definitely, partons will lose energy. And in fact, partons and jets will lose energy. And if you look at dijets, you have a trigger jet on one side and an away side jet or particles. These particles or jets on the away side of a trigger particle or jet will in fact have less energy. And he even said that on the away side, it would get fully absorbed. I come back to this in a minute. Just 10 years later, so Gilassi, Plummer, and Wang said, okay, here's the RAA that you're familiar with. As a function of PT, if you look at nucleus AB, they called it, you would see a suppression compared at zero impact parameter. In fact, compared to, let's say, less central collisions. And also, if they include quenching, shadowing, whatever, that in fact the RAA would be highly suppressed. So this was actually the first set of papers saying that high PD particles should be suppressed. Of course, that is seen in STAR above, with the beam energy scan above and including about 39 GeV in root S. And also at the LHC, one sees that all the experiments at the LHC measure the same RAA distribution out to about 100 GeV or so. So that's some consistency, let's say. And then if you compare LHC, which is in red here, with RHIC, which are Phoenix and Star, you see some slight difference where it appears that the LHC suppression's just a little bit stronger. Now that was for charged particles in lead-lead and gold-gold collisions. If you look at P-lead, there's no suppression compared to lead-lead at the LHC. Likewise, one of the first papers was the direct photons from Phoenix in the gold-gold central collisions, and there they saw that RAA was 1 compared to the pi zeros and the etas. And Alice showed also that that is the case for photons not, actually this is CMS showing the photons not being suppressed, but Alice also showed that the spectra for RAA for the different types of particles is quite interesting in itself. Okay, so I think the other thing is from all of this information on particles and jets, which I will still mention a little bit more about, Jetscape has tried, and I think this is one of the next goals, let's put it the next 5 years or so, of trying to measure the Q hat over T cubed. That's the parton energy loss per unit length in the plasma or in whatever it's traversing, whether it's cold or hot. And they've made predictions here from the JET collaboration and Jetscape using different inputs. And I think it's important, and this is really a task, I would say, for the field, is to try and figure out, and I know many of you are doing this already, what the path length is that the parton has traversed. And then you measure its energy loss. That's the next question, which I'll address in a minute. Okay, in terms of dependence. There is a flavor dependence, which appears to be, if you look here, that in fact the charged particles have the most suppression, and then you go up to pions. I'm not pointing to these all directly, but I think kaons are not in this plot, but you have pions and kaons. And then if you looked at the protons on the previous slide, they have a strong momentum dependence, which is interesting in itself, below 10 GeV, which has to do with recombination. And then as you get heavier, you see that J psis have the least suppression, and there are Ds in between the light quark mesons and the J psi. Okay, so now we're almost at Kong's midpoint, which I will wake you up in a minute, I hope. Okay, so back to Bjorkane and star data. Remember I said, Bjorkane said that if you have one jet on one side, the away side will be absorbed. Well, this is one of the first findings in star. And in fact, this is a trigger particle as a function of, this is a delta phi azimuthal angle difference between the trigger particle and what we call the away side, 180 degrees away. And one sees that in PP minimum bias, you have a nice away side peak and near side peak. However, in central gold in blue here, you see the away side suppressed. And this was one of our seminal papers on the quenching of the away side jet following these predictions by Bjorkane. Okay, so since I mentioned jets, let me just say, if you look at REA of charged particles and jets, I'm sorry, I'm in your way all the time, right?
It's okay.
Maybe
I can see it over here anyway.
You see that the charged particles at low PT, are suppressed, as are jets. Jets continue out here. The thing to remember with jets, though, is that and if you want to compare charged particles and jets, the jet includes many charged particles, and you have to look at the fragmentation function of the jet of a given momentum, and then say how many charged particles of this momentum are there in whatever the jets are that are making those charged particles. So you can't really compare jets to charged particles without folding in the fragmentation function for jets going to charged particles. Easy to say, not as easy to do, right? Except if you take the average, on average, the fragmentation function gives you roughly half of the momentum for a particle that's in a jet that has a parton that initiated it of that full momentum, or twice the particle momentum. Very, very rough. Okay, but the thing I want to point out here, in particular, is here are jets measured in star. Here are jets measured in ALICE, ATLAS, and CMS. You see the gap. This gap corresponds to, I'm sure, some of the data that you're analyzing now, trying to get up above 30 JeV for jets at RHIC. S-Phoenix will be a major contributor to that. And in ALICE in particular, at the LHC, trying to get below 50 JeV jets, all right? So that's a hole that needs to be filled. The other thing I wanted to point out is, here's some very nice data from ATLAS. If you look at the photon jet REA, so there's photon on one side, jet on the other side, as a function of centrality, that the REA is most suppressed, as you would expect, for the away side jet, for the most central collisions. And then as you get more peripheral, it becomes less suppressed. But the really interesting thing in this plot is that the inclusive jet, meaning not the photon on one side in the jet, but the jet on one side, the jet on the other, in fact, is even more suppressed. And so one has to think about, and I will tell you because it's something that I asked on my quiz. Anyway, quite easy to think about though, and we can discuss it if you like. I mean, the quiz isn't that important, in my view. Right, so the big difference here is inclusive jets are more suppressed than jets on the wayside of a photon. All right? So there's a difference there. All right, so this is the part where you need to wake up again. Because I would think, first of all, there were things measurements that were totally unanticipated. Now, we were measuring collective flow already, but we didn't anticipate the results that we ended up getting, or at least the impact of them. And then there's this whole list, and you see others as well, that have come on the market very recently, and I would like to think that, let me just address the juniors here and semi-juniors, that we'll get a lot more information on these different potential signatures. I hate to use the word signature so loosely though. Okay, so let's look at collective flow, and then I'm really just going to run down the list on the others. The real interesting thing with collective flow was that we didn't really anticipate after the first 5 years at RHIC that it would have such an impact and already be labeled as a nearly perfect fluid. So let me quickly say some of its properties. I mean, so the measurements since then as well, if you look at the LHC and you look at results from even the lowest energy that's plotted here from the beam energy scan, 39 GeV, that the V2 in fact follows the same curve as a function of PT. I don't think we expected that at all, first of all. And there was constituent quark scaling. This is star data of the various identified particles in flow, and that this really says that, okay, if the V2 scales as a number of constituent quarks, that the flow is being developed while you're still in the quark-gluon plasma phase. So that was quite interesting. Then it was also interesting, and I won't go into this because there are various interpretations on how the V2 goes negative. I'm happy to talk about that later if you like, or how it increases here, kind of flattens out. But the main thing I want to point out is if one comes along with second order viscous hydro and sees that the shear viscosity to entropy ratio is very near what was predicted to be the quantum lower bound of around 0.1. And these are fits to data, and there have been various other fits which range from 0.1 to 0.2 on that. But in any case, it's way down there, eta over S, compared to anything else that's been seen in real life, let's call it. And in fact, this really indicates that the QGP must be a strongly coupled fluid. We were just kind of trying to look at the collective flow and say, okay, there's collectivity there, but we never anticipated the impact and the results that have come out since, also with the help of theorists, of course. Okay, so now I'm going to start moving a little bit faster because I'm sure you are aware of the fact that jet substructure has become quite popular, and one can try to separate out the different legs of the fragmentation or the dynamical propagation of quarks and gluons in the jet. Now what I just said is a tall task. And I just list some of the initial papers. And this has really become popular in the last 5 years. Likewise, balloon plane trying to separate out, collisions and jets into, the momentum transfer and the radius size plane, where one can look at wide splittings, narrow splittings, hard collinear splittings, soft wide angle radiation, et cetera, et cetera. So one can go use the Lund plane and use some of the parameters like anti-KT and some of the scaling properties to try and separate things out in the Lund plane and get a better indication of what's going on. Energy correlators are quite new. I know, look, I mentioned these. I know various members in STAR are doing these calculations as well, trying to look at the energy flow within jets to understand, the part-time propagation, and let's hope eventually to understand the part-time energy loss in the quark gluon plasma and get some of its properties via those analyses. Okay, does size really matter? That's a real question in the overall scaling of things. If you look at V2 over the ellipticity for various systems, this is a compilation from STAR. One sees that it follows in 1 over n to the 1/3. And in fact, if you look at the RAA as a function of various systems, this is from Phoenix. It doesn't seem to change that much at mid rapidity. So what's going on? It only depends on, in part, I would say, so multiplicity makes a difference here, which means that centrality and in part make a difference. And to me, the big question is, what about PP? High multiplicity PP, for example, getting 100 particles from CMS in a PP collision is quite intriguing. I mean, what's going on? First of all, to get that many particles out of PP collisions. Second of all, does it have properties? And it appears that there may be some properties that are reminiscent, let's say, at least of those of a quark gluon plasma. And I think if that happens, if one can show that you have let's say somehow in the next 10 years we show there's a quark gluon plasma in very high multiplicity PP, I think a lot of the things I mentioned already, some of these paradigms have to change about the quark gluon plasma. Okay. Now, the equation of state, it's quite interesting because the beam energy scan is looking to see, what's going on with the phase, whether there's a critical point, and also at higher energies, even in STAR now, I think there are measurements trying to look at the speed of sound in the quark gluon plasma. And of course, we want to know the transport properties and understand the equation of state and what its variables are. And there's been a recent connection with binary neutron star mergers. And I know as far back as 5 to 8 years ago, there were predictions in some dynamical models that in binary neutron star mergers, even before they were seen, there could be a high density phase that could resemble what's seen in heavy ion collisions. Now, this may not be at RHIC or LHC energies, it could be at fair energies. At least that's what it's kind of pointing to right now. But I think this is all quite new in the last couple of years, and we'll need to keep an eye on it. Okay, unanticipated. Yeah, it's interesting because baryon junctions seem to come and go, meaning not experimentally, but theoretically. They're somehow popular in understanding PP in the 70s. I think Miklos Galassi in the 90s got interested in it again, and there are a couple of papers And then star comes along and makes this measurement. And one sees that if you take the net baryon number, the net charge, basically the net charge difference is the big point here, when looking at ruthenium versus zirconium collisions, that in fact, compared to various models, the data are significantly higher. So, in fact, by what appears to be at least a factor of 2, suggesting that it's not valence quarks that are causing this, but perhaps baryon junctions. Okay, and so I think this is new and interesting and still, needs more work. I'm not saying that the data need more work, but I think we need to understand what's going on here. And the models need to understand what's going on here, because you see the models are way down here. Okay. And Trivedi gave this great presentation. I heard it at the winter workshop, and I presume it was quite similar at the first baryon dynamics workshop. And I stole this slide from him because, in terms of baryon junctions, he pointed out that there's a bright future in various experiments. And I refer you to either of his talks to look into it more if you want to understand how baryon junctions might be investigated, in everywhere from JLab to EIC, Volterra data, and RHIC. Okay, I'm almost there. This was predicted, by Dockschitzer et al., that there should be a dead cone if you have a heavy quark in a jet, and that, in fact, there will be suppression of gluon emissions in a cone around, with an angle, the mass of the quark over the energy of the radiator that's coming out. And so, in fact, Alice has gone and measured this in pp, and they find for a certain energy range for the photons coming out, that in fact for charm quarks in pp jets, that there's a 7.7 sigma significance. And this is the paper if you want to refer to it and take a look. But the real interesting thing now is whether one can go and look and has the statistics and the ability in the heavy ion environment in AA to see whether this dead cone exists, and if so, that might give us more information on how partons propagate through the plasma. Okay. All right, and then this is a star measurement that was made, a little less than 10 years ago or so, but it was quite interesting and still stands. This whole idea of a vortical flow with a spinning quark-gluon plasma, which is quite easy to understand. If you have two charged bodies passing by each other, you're going to set up, a spinning interaction region here, and that in the local fluid center of mass, you're going to have various directions that depend upon the location of the particles in this spinning, let's call it quark-gluon plasma, and also the angular momentum that's set up by the impact parameter of the initial collision itself. All quite interesting, and a super nice result from STAR in Nature, looking at the lambdas, which have their own intrinsic spin. Okay, exotic nuclei. Well, both Alice and Star, and I'll have a couple of quotations. This is Star early on, making measurements of the hypertriton and then the nuclei anti-alpha in particular, anti-helium-3, And first of all, one sees that this is all consistent with coalescence and thermal models. I just show you here the signal, which looks strong and is convincing in the helium-3 pi- channel. And one can go ahead and look at the anti-hypertriton. This is from a more recent STAR publication, where one sees that the pi plus, the anti-deuteron, antiproton, in fact, from the anti-hypertriton, in fact, has been measured, and the mass difference between the hypertriton and the anti-hypertriton is quite interesting, and a new measurement in physics. So I should also, I can't go without pointing out these multi-quark states that have been recently measured and discovered at the LHC, in LHCb. Here is first observation of the doubly charged tetraquark and its neutral particle, and you can start adding up. They've labeled, I just took the simplest graphic that they have. You can look at the different quarks and combine them and see that in fact this is the doubly charged tetraquark. Likewise, they have measured the pentaquark. And, you know, we've talked about pentaquarks. We tried to measure pentaquarks in STAR over the years, but this signal is pretty convincing here of the 4.383 or 4.338 GeV pentaquark. You can kind of see, you know, okay, I can take UDS, that's a lambda, and a CC bar, that's a J psi. Okay. So I can look at and see, you know, what the, on a Armenteros plot, you know, where I see peaks, and then they see this nice peak when they project it down to the J psi lambda axis. Quite interesting, and I think there's a lot more to do there. Maybe those are out of the range of RHIC and STAR. I mentioned DCCs having not been seen. DICs are a whole different story. Elise has come and measured this difference between neutral and charged kaons that's significant, and this brings up this whole story of disoriented isospin condensates, and I just list a bunch of publications here, with the most recent by Joe Capusta et al. And the Alice publication, which shows a potential DIC signal. CME, you know, I hesitated to show any of these asymmetries because I still think, and you should correct me if I'm wrong, that there's still some question, and even here, STAR is looking into, where's the most recent publication? Anyway, backgrounds that are involved in trying to understand what's going on with the CME. And then I think I'm going to close now because there were many topics that I didn't talk about. I listed a lot that weren't anticipated. It's quite interesting because you see that I think there were some basic variables that had been worked on by theorists in the 10 to 15 years before RHIC started up, and there was kind of a consensus on that, how those should behave if you made a plasma or if you didn't make a plasma. And some of them really appear to come true. I can't, you know, one can ask, have we made a quark-gluon plasma? And I can tell you all the properties of the quark-gluon plasma. I can tell you what's been measured. You know, I can tell you that quarks appear to be deconfined when we make this measurement. There's no other way to explain it. I can say that about quarkonia. I can say that about the collective flow. I can say that about maybe one or two other things, you know, but everyone's always asking, is there a smoking gun, you know, and do we know the perpetrator? So this whole list of 10 things that I showed you just recently, and then this list, which I didn't say much about at all. I'm not saying that they're all candidates for signatures, but I think there's a lot of work that's still ongoing, and I think that there's a lot more that can be added, in particular with some of the new observables of the last 5 years. So I think I'll close with that, and I thank you. And I apologize if I didn't mention something, but tell me about it, and I'll try it next time. Thank you.
Thanks, John. Any questions from the room? We might need a minute to digest. Okay, Gregory?
Yes, I'm Gregory. John, thank you very much. That's a very impressive overview of, really like very impressive. What is your opinion? What is conceptually missing nowadays? Is it the theoretical input or experimental? Because there are a lot of things that you mentioned, and indeed some of those were confirmed. Some of those are puzzling, which we do not see. What is conceptually missing?
That's a fabulous question, and I'll give you an answer, maybe. No, I have a very strong opinion about it, and turns out you may have seen me walking around with David Gross at Cork Matter. He asked me this question, okay? He's Nobel Prize 2004 for asymptotic freedom, and he was a keynote speaker at Cork Matter. And we were talking, and that's exactly what he asked. So, what's missing? I said theory, theory, theory. There's a lot of experiment that still can be done, but theory is way behind. The really cool thing is, he said, well, we need a program at the Institute for Theoretical Physics in Santa Barbara. In the meantime, we got 6 excellent young theorists to put together a proposal. It's going to happen March in 2026. Fabulous, like 9 weeks of, and it's a melding of all different, it's perturbative QCD, heavy ion physics. Neutron stars are kind of on a periphery, and then some real fundamental physics, like Juan Maldacena will come and talk about something, if he says something, then everybody listens, right? So my simple answer is theory, theory, theory. These experiments still, there's a lot to be done, and by 2026, they're not all going to be done, but there'll be another theory institute, 10 years later or so that they pick up on it. But I think the theory is way behind. Thanks for your question. Bill?
Just, part of your theme was that what did we expect going in? And just a comment I'd make there, the expectation was that the plasma would behave like a diffuse gas. So you wouldn't see anything like flow. So we really didn't know, building and designing STAR, what it was we were gonna find. And the other comment is the DCCs, in particular for the younger members of the collaboration, when we did the simulations for the barrel calorimeter, we had the trigger barrel at the same time. We thought we could maybe trigger on this ratio of charge to neutral particles, charged particles to photons. And there was a whole program and detector built by all our colleagues from India, the photon multiplicity detector that hung on the east side of STAR, that came, ran its program, never saw any sign of this, and went away. If we go out on a tour, you can still see where it hung on the east side. The frame is still there, but the detector is long gone. And the last comment on that is that what led a lot of the interest in that was a single cosmic ray air shower event that was taken, that seemed to have a dramatic asymmetry between charged and photons and charged pions. It even had a name. They called it the Centauro event. And there was a lot of effort that went into all of that. But for those that have been in STAR the last 10 years, you never would have seen any of this, because that detector came, it ran its program, and it went away.
No, that's a good point. And let me tie your first comment back to what I just said about theory. David Gross, in his 2004 Nobel Prize speech for, co-discovery of asymptotic freedom, actually mentioned the quark-gluon plasma. And yes, we were thinking that the plasma is freely interacting quarks and gluons. If you say that to some smart theorists, you will get pointed to some papers before RHIC came on that contradict that. I've done it and I've contradicted. That's why I say it. Be careful whom you say, what company you say it in. Anyway, okay. Other questions? Another, sure.
So when we look at the quark-gluon plasma, so to speak, because it's not a diffuses plasma, right? So one way to go is what STAR is doing, going to the lower energies. The other way around could be go to the higher energies, right? What would be interesting, is there a need to go to even higher energies? Or, because some of the expectations, even when the RHIC started, have already been understood, because even if you run LHC, probably we're at the plateau somewhere there. Is there any particular reason to keep increasing energy, or we just need to focus more on some specific places where we are at right now?
Okay, my short answer is I think we need to focus more on, some of these measurements that I showed you at the experiments that are ongoing, and also FAIR, if it ever comes up, because I think there's a place for that. Going higher in energy, unless there's some new phenomenon. Let's say, okay, the only thing I could think of offhand, I never thought about going to higher energies, but this whole proton-proton high multiplicity game could be very interesting, if all of a sudden you had 1,000 particles coming out because you had 10 times the energy or so, then you might have a better idea of what the heck's going on, okay? But aside from that, and I would say that's kind of a new phenomenon, because I don't think it's explainable or even close to what we're seeing with heavy ions. At the LHC, you start looking at jets and high PG particles. You can quote me, I guess, to CMS and Atlas colleagues. I don't think you need to go there. I think you need to go high enough in energy. So I'm talking about particle energy. So I don't think you need to collide 1 GeV heavy nuclei, because I don't think you're going to get anything more interesting unless there's a new phenomenon again than with 100 GeV. Or you look at RHIC and you look at LHC, a lot of it's the same. Measurements come out to be the same, and I think one needs to really focus on, okay, my bias is to look inside jets and see what the heck's going on with partons as they propagate. You get higher in energy for the jet, the jet energy compared to the energy loss is huge. What you want is the energy loss of the partons to be similar to that of the jet, so we can start to take apart, what the components are of that energy loss. I'm kind of dreaming, honestly, because we haven't done that yet. I think it's pretty clear that FAIR, I don't know about BES, the lowest energies, and neutron star mergers may have some overlap. Now I know you're all going to go to my colleagues in Alice and said, John said that LHC you could forget, right? But it's frankly unfortunate, I will say, that RHIC is turning off. It's probably good for the machine because it's pretty old. But although one ring's going to be used for ESC, but they're going to renovate it. But I think RHIC really is in the energy range and has had the versatility, both in energy and the ions, that have not been explored or possible at the LHC. LHC is run by high energy physicists, so, you know, RHIC is the machine, period.
Okay, any questions from the Zoom?
Maybe I can ask.
Oh, Roman.
Romer.
Yeah, maybe a politically not so correct question. So what do you think? What's the end game, or
Where?
I mean, for the field, if there is one, or maybe say if you do this a third version of this paper, what do you wish to see in the next, I don't know, 5-10 years?
Right.
What we should measure experimentally? Of course, I mean, you say theory, we should catch up. Experimentally, where we're still missing.
Well, first of all, I hope to be alive to do it, you know, and aware and cogent. But I'm definitely intrigued by this PP high multiplicity stuff because I can't see how that ties to heavy ions, and maybe it's totally new phenomenon. But I think one does need, and it's not easy to go from PP to AA and understand everything, you know, and I worry about jets a little bit unless we can take them apart and understand what's going on in terms of parton energy loss and what's the constituents and components. I'm a little worried that that won't get us too far unless we know that, and that would be a goal in that game. You know, whether it's with energy correlations or, you know, using the Lund plane to separate out different types of collisions and then looking at the energy loss. I mean, I find everything interesting still. You know, I don't know that it's the end game, but, you know, you look at these LHCb results. I mean, we've been looking for pentaquarks forever. And then all of a sudden they pop out this, you know, this pentaquark, and it's there, you know, and they have tetraquarks now. And that's pretty fascinating to me, okay? And that's not so much heavy ions, but, you know, whether, of course, you would think it could be made more frequently in heavy ion collisions, but you got to make a lot of collisions. So what is the end game? In my view, from the beginning, like starting at the Bevelak, Bill will remember the equation of state. Have to understand the equation of state of nuclear matter is a function of density, you know, and what the incompressibility constant is for it, and, you know, speed of sound, all of these variables, that's nuclear physics, okay? So now maybe I'm too old school in that sense, but, you know, likewise with the quark gluon plasma, it's there. We have to understand its equation of state. You know, what's the speed of sound there? What can we do to it to understand its variables, how they depend on each other? I think that's a tall task. And with RHIC shutting down, I don't know, there probably won't be a third paper from me. I'm kidding a little because there's a lot to do, and the data from STAR and S-Phoenix will be quite useful, yeah. And then there's EIC, but it's not heavy ions.
Yeah.
Long answer, sorry, but you know, there's no single answer.
Okay, maybe last question for Zach.
On that last point, do you see any future for the field in this energy range in like a fixed target program at the EIC?
If I see any future, if you're asking me theoretically, conceptually, yes, but if you're asking me whether anyone will allow it, I don't know. You know, that could be a future generation proposal 10 years from now or a little more. Once EIC is running, I think that's the big worry now. Let's get EIC running. Unfortunately, let's get RHIC out of the way. But, you know, I think I wouldn't give up on heavy ions, let's say, once EIC is running. And I'm talking about not just LHC, but There are cosmic ray events. Who knows? I think there's a lot of room still for innovation, not just in the analysis, some of the analyses I pointed out, but in thinking of new experiments and how to use, what exists already, be it the EIC in 20 years or what have you. I wouldn't give up hope. Just the first day, don't ask the question.
Why not, John? I mean, why not stick a fixed target in? We've shown in STAR that putting the fixed target in the beam pipe doesn't hurt. So
No,
why
I
should
didn't
we wait?
say, I didn't say you shouldn't do it. I said, I doubt the first day they're going to want to hear you say, I want to do it. That's all.
But isn't this like a detector 2 prime target?
Isn't
Something
this a
novel?
what?
Like a second detector novelty? I mean, you're building a detector that is
Sure.
prime for fixed
That's a good
target,
point.
right?
Yeah.
I mean, EA is almost fixed target, right? So,
If you're invited to give another proposal, you can always propose whatever you think is best and include whatever you think will make good measurements. Yeah, I agree with you, Helen. If you're not invited, I'm not sure you'll get much traction initially. But you can start talking about it. Sure.
Okay, we should cut it up there. You can always find John during the coffee break, which we'll have now. Let's thank him one more time.